So in the last class, we have already come across the paramagnet at a given temperature, which is obeyed as the canonical ensemble, where the energy exchange can be possible. And the system, if kept at a fixed temperature when it is in thermal equilibrium with much larger system, or we usually call it a heat bath. Clearly, the energy of the system under discussion is not constant, and since the system is in thermal contact with the heat bath, so that it may exchange energy with it. So this is the normal phenomena of canonical ensemble. Now we are considering the paramagnet, which is at a given temperature, right? So uh, that will be proportional to the Boltzmann factor, that is e to the power minus E upon kT, where capital E is the energy of the small system. And subsequently, we have followed that the isolated paramagnetic system, the single spin satisfies the Boltzmann distribution in a state of equilibrium. So, derivation for the probability as well as the energy for the microscopic state for n spins, we have calculated already the partition function and the related thermodynamic quantities like pressure, magnetization, etc. How does it related to the partition function, such as E is equals to let me show you. Okay, this is the partition function Z, which is the average, which is the um, most important concept in terms of the partition function, which is summation over all microscopic states e to the power minus beta E. E is also over all microscopic state, and from that we can calculate the average energy at temperature capital T is an ordinary average with probabilities P is equals to Z inverse e to the power minus beta E, and followed that average energy can be calculated as minus 1 upon Z del Z del beta, that is minus del del beta of ln Z. And in a similar manner, it is possible to write the average magnetization in the form average of M is equals to 1 upon beta del H of ln Z. So depending upon that, can we calculate the following problem as I mentioned here is the basics of the paramagnet at a given temperature, and with J, or the total angular momentum, is greater than half. So the problem is calculate the partition function, right, for a paramagnet with general J. The second problem is calculate the average magnetization per spin and sketch it as a function of magnetic field H. C is calculate the susceptibility and compare it with that we calculated for J is equals to half. And the fourth one is calculate the specific heat CH and compare it with the result for J is equals to half. So this is the exercise for today, and we will discuss it now, how to calculate it, right? So to start with the problem, we have to write the partition function, right? So partition function per ion, that is small z. Do not confuse with z with the capital Z. This is the partition function for a single spin either, or a partition function for per ion. So small z is equals to sum over sigma I is equals to minus 2j to plus 2j e to the power beta g mu b h times sigma I divided by 2. The summation can be computed as a geometric series whose first term is, right, first term is e to the power uh, beta g mu b h times j. If we denote this as x is equals to beta g mu b times h, then this can be written as small z is equals to summation sigma I is equals to minus 2j to 2j e to the power x sigma I divided by 2, that is e to the power x j plus 1 minus e to the power minus xj divided by e to the power x minus 1. You have to remember the mathematical formula that 1 plus q square plus q to the power n minus 1 is equals to q to the power n minus 1 divided by q minus 1. Note that sigma I changes in steps of 2, right? So multiplying the numerator and the denominator in the last fraction by e to the power minus x by j, it turns out that small z is equals to e to the power x j plus half minus e to the power minus x j plus half divided by e to the power x by 2 minus e to the power minus x by 2, which is nothing but the sine hyperbolic series. Sine hyperbolic j plus half x divided by sine hyperbolic x by 2. So this is the partition function per ion. Now, if the number of spins is capital N, then the system's partition function is obtained as capital Z is equals to small z to the power n that we have already discussed. Then the expression becomes this thing to the power n. So this is the answer to the first problem. The second problem we have to do by this way, that the average magnetization per spin is calculated in a manner similar to that for the case of spin half. So we continue to express capital Z in terms of x, and in order to obtain the derivative with respect to h, we use the chain rule, right? So average magnetization over n is equals to 1 upon n 1 upon beta del del h of ln z, that is 1 upon n 1 upon beta d ln z dx times del x del h. So this is the chain rule here we apply. So we have discussed that we have denoted x is equals to beta g mu b h. So del x del h turns out to be beta g mu b, right? So this is substituted here in the expression. So beta cancels out, and in the derivative n also cancels out. So this is g mu b ddx of ln sine hyperbolic j plus half x divided by sine hyperbolic x by 2. So if we calculate by ddx of ln, this simply j plus half cos hyperbolic j plus half x divided by sine hyperbolic j plus half x minus half cos hyperbolic x by 2 divided by sine hyperbolic x by 2. Now we define the Brillouin function by b suffix jx is equals to 1 upon j plus half cot hyperbolic j plus half x minus half cot hyperbolic x by 2. And we can write the previous expression of average magnetization over n in terms of Brillouin function by g mu bj bjx, or using the definition of x, one can write the average magnetization over n is equals to g mu bj bj. Substituting the value of x, it is beta g mu bh, this way, right? So in order to plot a function of average magnetization per spin as a function of magnetic field H, we have to analyze the behavior of the Brillouin function Bjx. Since it is an odd function, right? So this is odd hyperbolic x minus this. So this is obviously a odd function, and it is sufficient to study the region for x greater or equals to 0. For x tending to infinity, it is easy to see that bjx tending to 1, right? It turns out to be like this. So for x tending to infinity, it is easy to see that bjx tending to 1. So this means that the saturation value of average magnetization per spin is g mu bj simply. As first sight, it seems that bjx diverges for x tending to 0. However, we know that for j is equals to half, bjx is simply tan hyperbolic x, which behaves like x at very small x, right? For j is equals to half, bjx is simply tan hyperbolic x, and this is the function which for small x, it behaves like almost like x. So we have to study its behavior near the origin more carefully, and we expand bjx around x equals to 0, and we can write cot hyperbolic y is nothing but cosine hyperbolic y divided by sine hyperbolic y. The uh, denominator of both sine and cosine is 2, so this is cancels out, and eventually it becomes e to the power y plus e to the power minus y divided by e to the power y minus e to the power minus y, which is 2 plus y square plus dot dot, and divided by 2y plus y cube by 3 plus dot dot. So for y far smaller than 1, it is possible to write cot hyperbolic y nearly equals to 1 plus y square divided by 2 divided by y. After getting common of y, it is 1 plus y square by 6. So for y far smaller than 1, this 1 divided by 1 plus y square by 6 simply becomes 1 minus y square by 6. If we substitute here, it becomes cot hyperbolic y is equals to 1 upon y times 1 plus y square by 2 times 1 minus y square divided by 6. So by neglecting the terms of higher order than y square, this cot hyperbolic y becomes 1 upon y simply times 1 upon y square plus 3 divided by, that is 1 upon y plus y by 3. Simple calculation. So for small x, the function or the Brillouin function bjx takes the form bjx is equals to 1 upon j plus half 1 plus 1 divided by j plus half x plus 1/3 of y, that is j plus half x, minus half 2 by x plus x by 6, which is 1 upon j 1/3 j plus half whole square times x minus 1/12 of x, that is x upon 3j times j square plus j, which is j plus 1 divided by 3 times x. And this is the behavior we already know, but the case j is equals to half. Now, still we have to check if indeed nothing special happens between x equals to 0 and x tending to infinity. To this end, we calculate the derivative of bjx with respect to x, which is minus j plus of whole square divided by j times sine hyperbolic square j plus half x plus 1 upon 4j sine hyperbolic square x by 2. So a brief study reveals that djx divided by dx is, or the ddx of Brillouin function is positive for all x. So bjx is a monotonic increasing function in the region under discussion. So hence the average magnetization per spin or divided by n as a function of h will look as the following plot, right? For j is equals to half, j is equals to 2, and j is equals to 7 by 2. So all we have used to arrive at the qualitative form of these curves is that the value at which they saturate increases in proportion to j, right? The expression gives us this j plus 1 divided by 3 times x. So, and their slope at the origin is proportional to j times j plus 1, right? J times j plus 1. So we quickly move on to the third problem, and we obtain the susceptibility from the behavior of average magnetization at small field, and we get average magnetization divided by n is nearly equals to g mu b j times j plus 1 divided by 3 times beta g mu b h, that is g mu b whole square times j times j plus 1 divided by 3 kt times h, and the susceptibility becomes g mu b whole square j into j plus 1 divided by 3 kt. Substituting j is equals to half and g small g is equals to 2, we obtain the result we have previously followed. That is the curve of susceptibility is look like. Where is the curve? I don't know. Let me. Okay, this is the susceptibility. No, no. So this is the susceptibility curve for average sigma as a function of X is equals to beta mu b h. So we get the value of chi as mu b square divided by kt, and the existence of an inverse relationship between the susceptibility and the temperature was actually found experimentally by P. Curie in 1895, and since then it is referred to as the Curie law of paramagnetism, right? And finally, for the next problem, we have to go to the next problem. Okay, problem D, where we have to calculate the specific heat at a constant field, which is Ch is equals to 1 upon n times del E del T H constant, and that is equals to minus 1 upon n k beta square del E del beta constant H, that is 1 upon n k beta square del beta of ln z, which is k beta square del 2 ln z divided by del beta square. This is small z obviously, where we have substituted capital Z is equals to small z to the power n, and we note that del 2 ln z del beta square is equals to g mu b h whole square times d2 ln z dx square. But we have already computed the derivative d ln z dx, and using it we obtain d ln z dx is equals to j times bjx. So d2 ln z dx square is equals to j times dbjx dx, that is minus j plus half whole thing square divided by sine hyperbolic square j plus half x plus 1/4 divided by sine hyperbolic square x by 2. So that finally the specific heat at constant field is equals to k times beta g mu b h whole thing square 1 upon 4 sine hyperbolic square half beta g mu b h minus j plus half whole thing square sine hyperbolic square j plus half beta g mu b h. So substituting j is equals to half and g is equals to 2, we can also obtain the previously calculated value of CH is equals to mu b square h square divided by kt square cos hyperbolic square beta g mu b h, right? So the functional behavior is again look like, wait a moment, this is the curve for the specific heat with kt divided by mu bh, and this behavior we have already discussed uh, previous in the previous class, right? The nature dependent upon the whether it is high temperature or low temperature, and it gives a peak around temperature like this. So this is the solution of the problem we have mentioned. So we are discussing another problem. The problem is it is possible to describe the behavior of certain materials in nature by spins with magnetic moment small m, which can point in three possible directions, all in one plane as depicted in the figure. This, and this. So all is separated by 2 pi by 3 angle. The first question is calculate the energy of a single spin in each of the above states in the presence of an external magnetic field. Capital H is equals to H, vector H is equals to H in the direction of the X cap. The second problem is a paramagnet whose constituents are spins of the type described above at temperature T. There is no interaction between the spins. Find its partition function when an external magnetic field is applied along X, And the third problem is find the average magnetization per spin in the paramagnet described in the previous problem, and calculate the value of the magnetization using two methods, as a canonical weighted average of the moment of a single spin and by direct calculation from the partition function. So we have to solve this by like this. The energy of a magnetic moment, that is small m, in a field H, capital H vector, is given by epsilon is equals to minus m dot h, that is minus mh cosine of alpha, and the alpha is the angle between the magnetic moment and the field. Substituting the value of alpha into each of the possible states, we find E of alpha is equals to minus mh, for which alpha is equals to 0, mh by 2 for alpha is equals to 2 pi by 3, and mh by 2 for alpha is equals to 4 pi by 3. So this is the solution, simple solution of problem A. The second problem is, since the temperature is given, it is natural to use the canonical ensemble, and the partition function is capital Z is a function of beta h is equals to summation over all states e to the power minus beta e over all state. So the same argument that led to the previous equation, which is based solely on the fact that the spins are independent, will yield for the paramagnetic system under discussion as well. And capital Z beta h is equals to small z beta h to the power n, where capital N is the number of spins in the system and small z is the single spin partition function. And in this case, small z is a function of beta h is equals to sum over alpha e to the power minus beta e is a function of alpha, where alpha is equals to none other than 0, 2 pi by 3, 4 pi by 3. So the energy per spin has already been calculated, and thus small z is equals to the power beta mh plus e to plus 2 e to the power minus beta mh by 2. From that we can calculate capital Z as this thing to the power n, right? So this thing I have already mentioned. So we are discussing the canonical ensemble and related thermodynamics. And for the paramagnetic system, we have calculated the partition function as well as the Helmholtz free energy. So the expression for the average energy, which can be calculated from the partition function of canonical ensemble, is nothing but minus del del beta of ln z, which can be represented also as kt square del del t of ln z. So if you use del del beta, then the sign is negative. Remember this. And if you use del del t, the sign is positive, and it is kt square, where beta is equals to 1 upon kt. Now we also know that pressure can also be calculated from partition function, which is positive quantity 1 upon beta del del v of ln z. And eventually from the thermodynamical identity one can calculate the entropy as 1 upon T is equals to del S del E. One can calculate the entropy as KLNZ plus E by T, right? So Helmholtz free energy is nothing but F is equals to minus KTLNZ, that is minus beta inverse LNZ, and the identities of free energy and the fundamental function of the canonical ensemble, which satisfies the equations of the free energy, one can calculate the other parameters as well. So as del f del t is equals to minus s, that is the time derivative of Helmholtz free energy gives the entropy with a negative sign. Since entropy is always non-negative, And one can also calculate the new, comparatively new function, that is mu, which is known as the chemical potential, which is minus T del S del N E and V constant, and which can be represented as del F del N T and V constant. Okay, so these are the basic formulae which can be calculated if you know, or if you can write the partition function of the system. So depending upon that, we can quickly go over to the harmonic oscillator and the Einstein solid, and what happens for the microscopic states of the of such system, that we have treated the paramagnet in a magnetic field in which each degree of freedom or each spin had a finite number of energy levels, 2 states per spin half or 2j plus 1 states per spin j. This kind of quantization is absent in the classical case, where the degrees of freedom have a continuum of values. So before treating such a problem, we treat an intermediate case in which the degrees of freedom take discrete values, but the number of different values is infinite. The case we shall treat here has also some practical applications for the calculation of the specific heat of solids, right? So for us, the quantum aspect is that the energy levels of the microscopic states take discrete values, and it may be worth mentioning once more that the fact in quantum theory the energy levels are discrete, which makes the statistical interpretation of such systems more natural than their classical counterparts. Okay, so a harmonic oscillator with angular frequency or angular velocity omega in place of the magnetic moment, one may think of a system as a lattice of mass m, each connected at the lattice side of a spring with a spring constant k, so that your angular velocity is nothing but root over k upon m, and atoms are oscillating around their equilibrium position. So when the oscillations are small, their motion is approximately harmonic, and we can write the partition function of the canonical ensemble in accordance with the previous theory derived, and discuss the states of a single oscillator. Now, because the system we are thinking of is a lattice of atoms, the oscillators discussed here are quantum oscillators. The quantum discussion of the harmonic oscillator may be summarized that the energy levels of the one-dimensional harmonic oscillator are characterized by a non-negative integer n, and one can write the uh, energy expression as n plus half h cut omega, where n takes the integer, positive integer values. So note that all the values of the epsilon n are positive, just for a classical oscillator, but this is where the similarity ends. The amplitude A, this is of a classical harmonic oscillator, can take a continuum of values, and hence its energy epsilon is equals to half m omega square a square, that is constant for classical oscillator, takes a continuum of values starting from the minimal value of epsilon is equals to 0. The energies of the quantum oscillator, however, are quantized in intervals of h cut omega, right? And starting from the minimal value, which is not 0, but epsilon is equals to half h cut omega. So as n increases, the energy of the oscillator increases like parabolic manner in terms of classical oscillator. So n as the degree of excitation of the oscillator. N characterizes the state of the oscillator, just as the number sigma used for the magnetic moment. So this is the figure representing the energy levels of a harmonic oscillator where the dashed discrete lines are the quantized levels and the full parabolic line is the energy of classical oscillator versus amplitude A. So the next step we can calculate is to investigate the microscopic states of a lattice of capital N harmonic oscillators as a whole. So since each oscillator is characterized by a degree of excitation small n, the microscopic state of capital N oscillators will be characterized by n degrees of excitation, that is n1 to nn, similar to the specifications of all the spin values in terms of n numbers, that is sigma 1 to sigma n in case of paramagnetic samples. The energy of a microscopic state in which oscillator 1 has a degree of excitation n1, the second a degree of excitation n2, and so on and so forth, will be the sum of all the oscillator energies, that is capital E is nothing but so capital E is a function of n1 to nn is nothing but the sum of individual oscillator energies, that is epsilon n1 plus epsilon n2 plus epsilon nn. So one can write the partition function of the oscillators, and capital Z is equal to summation n1 to nn e to the power minus beta e n1 nn, that is equals to summation n1 to nn, and one can write in terms of e can be right. One can write this e n1 n2 to nn is nothing but epsilon n1 plus epsilon n2 plus epsilon nn. So one can use this representation here. So this can be written as e to the power minus beta epsilon n1 to the power minus beta epsilon n2 dot 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 e to the power minus beta epsilon nn. And each summation variable varies from 0 to infinity. So one can write the sum of products as a product of sums, right? So in precisely the same way as we have used in the earlier cases, capital Z is equals to product of summation n1 is equals to 0 to infinity to the power minus beta h cut omega n1 plus half e to the power minus beta h cut omega n2 plus half, and so on and so forth, into dot 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 into e to the power summation nn to infinity e to the power minus beta h cut omega nn plus half, right? So since all the factors in the product on the right hand side are identical, we can write the partition function in the form z is equals to small z to the power n, where small z may be thought of as a partition function of a single oscillator, which can be written as summation n is equals to 0 to infinity to the power minus beta epsilon n, that is n equals to 0 to infinity to the power minus beta h cut omega n plus half, right? So this reduced to calculating the partition function of a single oscillator, which is nothing more than the summation of a geometric series small z is equals to e to the power minus beta h cut omega divided by 2 summation e to the power minus beta. I hadn't write yet. That is small z equals to e to the power minus beta h cut omega divided by 2 summation n equals to 0 to infinity e to the power minus beta h cut omega n. And what can be calculated this as e to the power minus beta h cut omega divided by 2 divided by 1 minus e to the power minus beta h cut omega. How do I calculate it? I know the sum of an infinite geometric series, which is summation n is equals to 0 to infinity x to the power n, is nothing but 1 upon 1 minus x for x less than 1. Right? So this can be written as simply this thing to the power minus 1. Now, to calculate the average energy of an oscillator, the result is this epsilon average is equals to h cut omega divided by 2 plus h cut omega divided by e to the power h cut omega upon kt minus 1. So one can prove this also. I am discussing that. So how do I prove that? Okay. Mm, yeah. So the average energy is given by energy average divided by n is the single particle oscillator energy average is nothing but minus del del beta of ln z. So okay, E is equals to minus del ln z del beta, that is minus n del ln small z del beta. So if I calculate the partition function for a single oscillator small z, which is nothing but this one, e to the power minus beta h cut omega, this one, 1 minus e to the power minus beta h cut omega to the power minus 1, and hence the average energy per oscillator, that is E upon n, can be derived directly from the single particle partition function as minus del del beta ln to the power minus beta h cut omega divided by 2 divided by 1 minus e to the power minus beta h cut omega, which is minus del del beta of minus beta h cut omega divided by 2 minus ln 1 minus to the power minus beta h cut omega, which is nothing but from this one can derive h cut omega by 2, and from the second part one can derive h cut omega divided by to the power h cut omega divided by kt minus 1, and we have substituted beta is equals to 1 upon kt, right? So yeah, this is another important aspect. And the interesting question is the average of the value of n, that is the excitation, the degree of excitation of the oscillator, is also represented as n average is equals to 1 upon e to the power h cut omega upon kt minus 1, which is the celebrated Bose-Einstein distribution, right? So the exercise is to prove this as the degree of excitation of the oscillator. Okay, from the two ways. The first is by direct calculation of the average, and second is from the average energy of an oscillator. So what is the approach? First, we derive the probability for a given oscillator to be in the nth energy level in a way similar to the calculation of the probability for a given magnetic moment to be found in the state sigma is equals to +1 and -1. Sigma is equals to +1 or sigma equals to -1. To do this, we recall the probability of a microscopic state I by the set of excitation number n1 to nn is nothing but p n1 to nn is equals to z inverse e to the power minus beta e n1 to nn. And now since E is the sum of single oscillator energies epsilon n, right? And capital Z is the product of n identical factors. We always use capital Z equals to small z to the power n, and we can write the probability for a microscopic state as the product of the n probabilities like Pn1, Pn2, Pnn, where Pn is simply small z inverse e to the power minus beta epsilon. So using the excitation probabilities, we calculate the average according to average n is equals to z inverse summation n equals to 0 n e to the power minus beta epsilon. So substituting this en and small z with the notation epsilon is equals to h cut omega, one can write this at e to the power minus beta epsilon by 2 summation n equals to 0 to infinity n e to the power minus beta n epsilon divided by e to the power minus beta epsilon by 2 summation n equals to 0 to infinity e to the power minus beta n epsilon. To calculate the right hand side, we use a trick similar to one have used in the calculation of the previous problem, and the numerator is the derivative of the denominator with respect to the variable x equals to beta epsilon. So we can write n as simply summation n equals to 0 to infinity So n can be written as minus ddx of ln e to the power summation n equals to 0 to infinity e to the power minus xn, which is minus ddx of ln 1 upon 1 minus e to the power minus x, which is nothing but e to the power minus x divided by 1 minus e to the power minus x, which is 1 upon e to the power x minus 1, right? This one. The value of average n is equals to 1 upon e to the power x minus 1. So substituting this x is equals to beta epsilon and beta is equals to 1 upon kt and epsilon is equals to h cut omega, one can write the average excitation is 1 upon e to the power minus h cut omega minus 1. The another way of doing this is the averaging for a given oscillator uh, from this theory. As I know, epsilon is equals to h cut omega divided by 2 plus n h cut omega. So one can write the averaging of both the sides, and which yields the average of h cut omega by 2 plus average of n h cut omega, which is h cut omega by 2 plus h omega average of n, and one can use the average value of the excitation, and finally the result can be reached. So another important aspect or the dependence of the n, analyzing the temperature dependence of the excitation, one find that this n approximately is equals to e to the power minus h cut omega by kt where low temperature limit, which is if temperature is low, by kT, the product of constant time temperature is far smaller than the h cut omega, and if temperature is high enough, then kT is far greater than h cut omega. For these two approximations, low temperature and high temperature, these value of the average of the excitation can take e to the power minus h cut omega by kT, or the exponential dependence, and simply kT upon h cut omega. So another exercise is prove that this average, this one, has the asymptotic behaviors. So how do I do that? So at low temperature, h cut omega by kT is far greater than 1, and the exponential dependence, this one is far greater than 1. So n can take a value e to the power minus h cut omega by kT. One, simply this, if this one, if my this value, exponential value, is far greater than 1, we can neglect this, then simply this becomes 1 upon this exponential, then which one can write as e to the power minus h cut omega by kT. And at high temperature, this ratio is far lesser than 1. That is, one can use the Taylor series expansion of exponential series, and the power expansion of the exponential series is nothing but 1 plus x square by factorial 2 plus dot. And to take only the first two terms, one can yield e to the power h cut omega by kT is equals to 1 plus h cut omega, this one. And so n can be written as 1 divided by 1 plus h cut omega by kT. Only two terms, the higher order terms of h cut omega, are neglected, minus 1. 1 cancels out. That is simply kT by h cut omega. So this is the typical dependence of the excitation versus the temperature dependence of the average degree of excitation of a harmonic oscillator, right? So at low temperatures, in this region, the n vanishes faster than any power of t. This means that the oscillator cannot be excited from its ground state n equals to 0, since the energy kT supplied by the heat bath is insufficient to overcome the difference h cut omega to the state n equals to 1. So in contrast, at high temperature states may be excited up to a certain value of n, given approximately by the thermal energy divided by h cut omega. Thus, we may expect that n takes the value of kT by h cut omega, which is the relation for high temperature. Right? And note that instead of saying that the oscillator is excited to a degree of excitation n, we say that there is n bosons of phonons, each with energy h cut omega. The calculation of average value of excitation is described in the language to be the average number of phonons as function of t, as this equation or this approximation for low temperature and high temperature states states that the phonons disappear as t tending to 0 and rapidly grow in number with increasing temperature. So this is a typical behavior of the graph. Your low temperature limit, the exponential function dominates, and the high temperature limit, this t becomes dominant. So as kT increases, this increases almost linearly. Now, common note to this problem is a system of capital N oscillators and a single oscillator for the calculation of thermal averages and one can thought of as an oscillator in thermal or the thermodynamic equilibrium with a heat bath with which it may exchange energy. So a single harmonic quantum oscillator resides in a container full of gas at a given temperature. The concept of single particle functions and the thermal averages with respect to such ensembles are to be understood from this point of view. So such a description is made possible by the absence of interaction between the oscillators. So another exercise is that depending upon the harmonic oscillator, yes, this is the another exercise which says that the question is, let us study the system of three identical oscillators, right? Each of them having three energy levels. Verify the previous two equations, that is the average, that is these two. This one, the sum of products is the product of sums, and this one, right? We can use these two equations to solve this. So how do I approach? The partition function in our example is obtained from this equation z is equals to e to the power minus beta n1, n2, n3, where each of the summation, that is n1, n2, n3 variables takes the values 0, 1 and 2. As the question reveals that each of the system of three identical oscillators and each of them having the three energy levels. Now the energy of a given state described by the triplet, that is n1, n2 and n3, one can write E n1, n2, n3 is equals to h cut omega, that is 3 by 2 plus n1 plus n2 plus n3, that is 3 by 2 h cut omega, which is common, plus h cut omega n1 plus n2 plus n3. Note that the first term 3 by 2 h cut omega is common to all states and is independent of the individual quantum numbers. So e to the power minus beta e n1, n2, n3 is equals to nothing but e to the power minus 3 beta epsilon divided by 2 e to the power minus beta n1 plus n2 plus n3 times epsilon, where we have denoted that h cut omega is equals to epsilon. So in order to find the partition function, we have to sum over all states of the system, and each oscillator has three possible states below the given. The system of three oscillators is nothing but 3 cubed, that is 27 microscopic states, which are described by all the triplets n1, n2, n3 in the following table. So n1, n2, n3 can take the value in the following manner: 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 1, 2, 0, 2, 2, 1, 2, 2, and 2, 2, 2. Then 0, 1, 0, 0, 2, 0, 0, 2, 1, 2, 0, 2, 2, 1, 2. Then 1, 0, 0, 2, 0, 0, 1, 0, 2, 2, 2, 0, 2, 2, 1. Then the next column 0, 1, 1, 1, 2, 0, 1, 1, 2. Then 1, 0, 1, 2, 0, 1, 1, 2, 1. Then 1, 1, 0, 2, 1, 0, 2, 1, 1. Then 1, 1, 1. So all 27 microscopic states can be revealed in this tabular form. Note that all the states that appear in the same row have the same energy. One can calculate this from n1 plus n2 plus n3 is 1 throughout. 2 throughout, 3 throughout, right? So to conclude, capital Z is equals to nothing but e to the power minus 3 beta epsilon divided by 2, 1 plus 3 e to the power minus beta epsilon plus 6 e to the power minus 2 beta epsilon plus 7 e to the power minus 3 beta epsilon plus 6 e to the power minus 4 beta epsilon plus 3 e to the power minus 5 beta epsilon plus e to the power minus 6 beta. It ends here. So from the cube of the single particle partition function for a single oscillator, by small z is equals to n equals to 0 to 2 e to the power minus beta epsilon n, which is e to the power minus beta epsilon by 2, 1 plus e to the power minus beta epsilon plus e to the power minus 2 beta epsilon. If one calculate this z cube with the identity, then 1 plus x plus y whole thing cube is equals to this series. And one can use this by simply the exponential power form, and the equation can be obtained. So this is one exercise. The second exercise is, this can be proved in the earlier section. Okay. So this is another problem. The problem is calculate the free energy of a harmonic oscillator as well as its entropy and sketch their temperature dependence. And the second one is, if the frequency of the oscillator is 10 to the power 13 second inverse, what is the transition temperature from low temperature behavior to high temperature behavior? Right? So the free energy of a single harmonic oscillator is nothing but Helmholtz free energy divided by the number of oscillators. That is the small f single harmonic oscillator is nothing but f by f is minus KTLN small z, where small z is the partition function, which can be written as e to the power minus beta h cut omega divided by 2 divided by 1 minus e to the power minus beta h cut omega. And hence small f is equals to h cut omega by 2 plus KTLN 1 minus e to the power minus h cut omega by k. So the entropy of a single harmonic oscillator is capital entropy divided by n, that is minus del f del t, that is minus k ln 1 minus e to the power minus h cut omega divided by kt minus kt times minus h cut omega divided by kt square e to the power minus h cut omega by kt divided by 1 minus e to the power minus h cut omega by kt. That is minus k ln 1 minus e to the power minus h cut omega by kt minus h cut omega by kt times 1 upon e to the power minus h cut, sorry, minus, not minus, to the power h cut omega by kt minus 1. So it is both, noting that we would have obtained the same result by using the relation entropy is equals to energy minus free energy divided by t, and the functional dependence of the free energy in units of h cut omega of a single harmonic oscillator as a function of the temperature in terms of h cut omega by k, like this manner. And the entropy takes the reverse trend. The entropy in units of k of a single harmonic oscillator as a function of the temperature in units of h cut omega by k, one can obtain this type of behavior. And for the second part, to calculate the transition temperature between the two types of behavior is in the region in which the quantity kt by h cut omega is not very large and not very small. That is, in the crossover region, this kt by h cut omega is nearly equals to 1. And this can also be seen from the both graphs above. And the transition temperature is thus T is equals to h cut omega divided by k, which is 10 to the power minus 34 into 10 to the power 13 into 2 pi divided by 1.4 into 10 to the power minus 23, which is 450 k.